In the unending silent blackness of the cosmos, our own sun is but one of 100 billion stars in a galaxy of 100 billion suns. For millennia, humanity has looked up into that abyss, feeling a profound and echoing solitude. We have painted our gods in the constellations, written our myths in the phases of the moon, and asked the same eternal question to the void, are we alone? The universe in its vast indifference has offered no reply. It has shown us worlds of fire and planets of ice. We have found gas giants larger than our wildest dreams, and dead pockmarked rocks sterilized by radiation. The heavens seem to be a gallery of extremes, a cosmic museum showcasing everything life is not. But in this grand silent theater, a faint whisper has finally begun to cut through the stillness. It emanates from a place surprisingly close, a mere stone's throw in the galactic neighborhood. The sound originates from an unassuming red star, a celestial ember glowing faintly in the constellation Puppis. This is the story of a message in a bottle, a gravitational signature traveling for 20 years to tell us of a world that might feel familiar. This is the story of Gliese 251c. It is a tale that challenges our sense of uniqueness and perhaps brings us one step closer to an answer. To understand the significance of this newfound world, we must first journey back in time to an era when the very idea of other planets was not science but heresy. For most of human history, the stars were fixed points of light divine decorations on a celestial sphere that revolved around us. Earth was the center of everything, a special, singular stage for the human drama to unfold. This comforting certainty was shattered by figures like Copernicus, Galileo, and Giordano Bruno, who dared to suggest that the stars were not lights but other suns. If they were other suns, then a revolutionary logic followed. Those distant suns might have their own families of planets. This concept was so radical, so profoundly destabilizing that Bruno was burned at the stake for it. For centuries, this notion of exoplanets remained in the realm of philosophy and science fiction. We lacked the tools to see them. Searching for a planet around another star was like trying to spot a firefly next to a brilliant searchlight from 100 miles away. The challenge seemed insurmountable. The direct light of the star would simply overwhelm any faint reflection from an orbiting companion. Scientists needed a new, more clever way to look. They decided not to search for the planet itself, but for the shadow it casts, the subtle influence it exerts. One of the most powerful of these indirect methods is known as the radial velocity technique. Imagine two dancers, a very large heavy person and a much smaller lighter partner waltzing together. They are holding hands, spinning around a common center of gravity. From a great distance in a dimly lit ballroom, you might only be able to see the larger dancer. You cannot spot their smaller companion, yet you know the partner is there. How? Because the large dancer is not standing still. They are swaying back and forth, moving in a small circle. Their movement is a response to the gravitational pull of the invisible partner they are swinging around. By carefully measuring the rhythm and scale of that sway, you could deduce the mass and orbit of the unseen dancer. This is precisely the principle behind the radial velocity method. A star like Gliese 251 is the large dancer. An orbiting planet like GJ 251c is the small unseen partner. As the planet revolves, its gravity tugs on the star, making the star wobble ever so slightly. From our vantage point on Earth, 20 light-years away, we can see this wobble. As the star moves toward us in its tiny dance, the light it emits is compressed, shifting toward the blue end of the spectrum. As it wobbles away from us, its light is stretched, shifting toward the red end of the spectrum. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound higher in pitch as it approaches and lower as it recedes. For decades, astronomers have been building instruments, spectrographs of incredible precision capable of detecting these minuscule rhythmic color shifts in starlight. It is a task of almost unimaginable delicacy. They are searching for a stellar wobble caused by an orbiting planet that is often no faster than a walking human's pace. Using the Carmenes instrument, a high-tech planet hunter in Spain, astronomers watched the faint red glow of Gliese 251. They measured its light night after night for years, and in the data, a clear periodic rhythm emerged, a sway, a celestial waltz. The star was not alone. The data revealed a partner, a world with a minimum mass about 4 times that of Earth, circling its star every 14.2 Earth days. The whisper from the darkness had been decoded. GJ 251c had been found. The world itself orbits a star very different from our own. Our Sun is a G-type yellow dwarf, a relatively rare and brilliant star. Gliese 251, however, is an M-dwarf, a red dwarf. These are the most common types of stars in the Milky Way, making up nearly 3/4 of the stellar population. They are the quiet, unassuming majority of the galaxy. Red dwarfs are small, cool, and incredibly long-lived. While our Sun will burn through its fuel in another 5 billion years, a red dwarf like Gliese 251 will sip at its hydrogen reserves for trillions of years, far longer than the current age of the universe. This cosmic longevity presents a tantalizing prospect. It offers an almost infinite amount of time for life to emerge and evolve an unbroken stretch of cosmic stability. But this stellar endurance comes at a price. Red dwarfs are notoriously tempestuous, especially in their youth. They are known to unleash powerful stellar flares, bursts of radiation and charged particles that are hundreds or even thousands of times more powerful than anything our own Sun produces. A single one of these superflares could strip the atmosphere from a nearby planet, boil its oceans, and sterilize its surface with X-rays and ultraviolet radiation. Any life on a world orbiting a red dwarf would need to be incredibly resilient or have a powerful magnetic field, a thick atmosphere, or perhaps seek refuge in the depths of an ocean. And there is another profound consequence of orbiting so close to a small dim star. Because Gliese 251 is so much cooler than our Sun, its habitable zone, the orbital region where temperatures are just right for liquid water to exist on a planet's surface, is nestled much closer to the star. GJ 251c orbits its star at a distance that would place it well inside the orbit of Mercury in our own solar system. This proximity creates a powerful gravitational relationship, leading to a phenomenon known as tidal locking. Much like how the Moon always shows the same face to Earth, a tidally locked planet would have one hemisphere perpetually baked in the star's light, and the other hemisphere eternally frozen in darkness. A world of two extremes, one side a scorched desert, the other a desolate land of ice. So when we hear the term super-Earth, what are we truly picturing? The name itself is a category of convenience, a placeholder for worlds that are more massive than Earth, but less massive than Neptune. This mass range, however, contains a universe of possibilities. Imagine a cosmic bakery where the universe uses fundamental ingredients like rock, iron, water, and gas to create planets. Earth is one specific recipe: a dense iron core, a rocky mantle, a thin crust, a veneer of water, and a wisp of a nitrogen-oxygen atmosphere. A super-Earth like GJ 251c could follow this recipe simply scaled up. It might be a terrestrial giant, a rocky world with 4 times Earth's mass. Its gravity would be significantly stronger. Mountains might not be able to grow as high before collapsing under their own weight. Trees, if they existed, would need to be incredibly strong and squat to support themselves. Any creatures would evolve to have stocky, powerful limbs. The sky might appear vast and close. Alternatively, GJ251c could be a water world. If the planet formed with a much higher proportion of water than Earth did, it could be a world without continents, a global ocean hundreds or even thousands of kilometers deep. In its crushing abyssal depths, exotic forms of high-pressure ice like Ice 7 or Ice X could form at the boundary of a rocky core. Life in such a place would be entirely aquatic, perhaps evolving in the warm currents near hydrothermal vents, completely oblivious to the star glowing in the sky above. There's a third, less promising possibility. GJ251c could be a mini Neptune. It might have a solid core, but one that is shrouded in an incredibly thick, crushing atmosphere of hydrogen and helium, a runaway greenhouse envelope that makes its surface utterly uninhabitable, more like a small gas giant than a large, rocky Earth. Distinguishing between these identities, rocky giant water world or gassy mini Neptune, is the critical next step in understanding this planet, and the answer lies in its atmosphere or lack thereof. The most tantalizing aspect of GJ251c is its location. It orbits squarely within its star's habitable zone. Let us explore this concept, this so-called Goldilocks zone, with more care. It is not merely a distance, but a delicate balance of energy. Think of a campfire on a cold, dark night. If you stand too close, the heat is unbearable. You are scorched. If you stand too far away, the cold bites at you and you freeze. But there is a perfect, comfortable ring around the fire, a temperate region where you are warmed but not burned. The habitable zone around a star is precisely this temperate ring. For a large, bright star, this zone is wide and far away. For a small, dim red dwarf like Gliese 251, this life-sustaining region is much narrower and drawn in very close. GJ251c orbits within this delicate band of warmth. The energy it receives from its star is just enough that if the planet has a suitable atmosphere, liquid water could theoretically pool on its surface. And where there is liquid water, there is the potential for life as we know it. But the tidal locking we mentioned earlier complicates this picture immensely. A planet with a permanent day side and a permanent night side sounds like a world doomed to be uninhabitable. The day side would heat up until oceans boiled away, while the night side would become so cold that the atmosphere itself would freeze and fall as snow, leaving a barren vacuum. However, nature is often more ingenious than our initial predictions. A sufficiently thick atmosphere could act as a global heat engine. Strong winds would perpetually circulate from the hot day side to the cold night side, redistributing thermal energy and moderating the temperatures on both hemispheres. Instead of a world of fire and ice, you might get a world of perpetual mild warmth on the day side and a chilly but not uninhabitable climate on the night side. The most fascinating real estate on such a world would be the region between these two extremes, the Terminator Zone. This is a permanent ring of twilight, separating eternal day from endless night. Imagine standing on the surface in this zone. The small red sun would hang motionless on the horizon, never rising, never setting. One half of the sky would be in perpetual reddish daylight. The other half would be a canopy of brilliant, unmoving stars. This twilight band could offer the most stable and clement conditions on the entire planet, a ribbon of habitability circling the globe. Rivers of meltwater could flow from the edge of the dayside ice cap. Photosynthetic life, if it existed, would be perfectly adapted to the low-light conditions of an eternal sunset. This has given rise to the captivating concept of an eyeball planet, a world with a liquid ocean on its day side, staring unblinkingly at its parent star. GJ 251c could be such a world. The discovery of this potential haven is made all the more profound by its proximity to us. 20 light-years. The number sounds immense, and in human terms it certainly is. 1 light-year is the distance light travels in a year, a journey of nearly 6 trillion miles, or 9.5 trillion kilometers. 20 light-years is roughly 120 trillion miles. The Voyager 1 spacecraft, our fastest and most distant emissary, travels at over 3,800 miles per hour. Even at that blistering speed, it would take Voyager more than 350,000 years to cross the Gulf to GJ 251c, so we will not be visiting anytime soon. But on a galactic scale, 20 light-years is our front porch. Our Milky Way galaxy is 1,000,000 light-years across. Most of the exoplanets discovered by missions like Kepler are hundreds or even thousands of light-years away. They are fascinating, but they are distant specks too far for us to study in any great detail. GJ 251c is different. Its closeness makes it a prime target for the next generation of astronomical instruments. It is a cosmic laboratory delivered to our doorstep. We are not the first to find a close neighbor. Just 4.2 light-years away orbits Proxima Centauri b, the closest known exoplanet to Earth. For a moment it was hailed as our greatest hope, but its star, Proxima Centauri, is a far more violent and angry red dwarf than Gliese 251. Proxima b is blasted by stellar winds, thousands of times more intense than those our Earth experiences. It is regularly scorched by flares that would render its surface lifeless. While we cannot rule out life on Proxima b, the conditions there appear to be extraordinarily hostile. Further out at about 40 light-years lies the famous TRAPPIST-1 system, a remarkable family of 7 Earth-sized rocky planets orbiting their own ultra-cool red dwarf star. Several of these worlds reside within the habitable zone, offering a stunning natural experiment in planetary formation. GJ 251c now joins this exclusive club of nearby potentially habitable worlds. It may not be as close as Proxima b nor part of a large family like the TRAPPIST-1 planets, but its star appears to be older and quieter. It may represent a calmer, more stable environment, a more promising candidate for life. It is a new character in the unfolding drama of our local interstellar neighborhood. The era of merely detecting these worlds is drawing to a close. We are now entering the age of characterization. The most powerful tool we have for this is the James Webb Space Telescope. This magnificent observatory, floating 1 million miles from Earth, is designed to see the universe in infrared light, the perfect wavelength for studying dim, cool stars like red dwarfs. One of Webb's primary missions is to perform what is known as transit spectroscopy. When a planet like GJ 251c passes in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us. Webb can capture this light and analyze its chemical composition. Think of it as a cosmic barcode scanner. As starlight passes through an atmosphere, different molecules, water, vapor, carbon dioxide, methane, oxygen, absorb specific wavelengths of light. Each molecule leaves a unique, telltale fingerprint, a dark line in the spectrum of the starlight. By analyzing which colors of light are missing, we can deduce what the planet's atmosphere is made of. It is a breathtakingly subtle measurement. We are attempting to analyze the air of a world 120 trillion miles away. This technique is our first real hope of answering the big questions. Does GJ 251c even have an atmosphere? If so, how thick is it? Does it contain water vapor, the most crucial ingredient for life? And most excitingly, could it contain biosignatures? These are gases like oxygen and methane in large quantities that are difficult to explain without the presence of biological processes. On Earth, our oxygen-rich atmosphere is a direct result of billions of years of photosynthesis by plants and microbes. Finding a similar signature on GJ251c would be the single most profound discovery in human history. It would be the first tangible evidence that life is not a unique miracle confined to our own small blue world. The James Webb Space Telescope is just the beginning. On the ground, a new generation of behemoths is under construction. Telescopes, like the extremely large telescope in Chile, with a primary mirror nearly 40 meters across, will have the light-gathering power and resolution to potentially do what was once thought impossible: directly image a planet like GJ251c. This would not be a detailed photograph like we have of Mars or Jupiter. At first, it would be a single pixel of light, a pale dot separated from the blinding glare of its star. But even that one pixel would be revolutionary. We could watch its color change as the planet rotates, allowing us to map the presence of continents, clouds, and oceans. We could see seasonal changes as ice caps grow and shrink. We would no longer be inferring a world from a gravitational wobble. We would be seeing it, however faintly, with our own eyes. And what if we saw something that hinted at more than just habitability? What if we found an atmosphere rich in industrial pollutants, gases like chlorofluorocarbons, that have no known natural source? This is the realm of searching for technosignatures, evidence of an advanced, technology-wielding civilization. The discovery of GJ251c provides an electrifying new target for programs like SETI, the search for extraterrestrial intelligence. For decades, radio telescopes have been scanning the skies, listening for an artificial signal, a structured broadcast that stands out from the cosmic static. Knowing that a potentially habitable world exists so close allows us to focus our listening efforts. We can aim our radio dishes at that specific point in the sky and listen with unprecedented sensitivity. Are we being broadcasted to "Is anyone home?" The silence we've experienced so far might not be because the galaxy is empty, but because we've been listening to random channels instead of calling a specific number. GJ251c gives us a number to call. This brings us to the ultimate question, the one that underpins this entire quest. What does it mean for us, for humanity, to find a second Earth? The discovery of a truly Earth-like world teeming with life would fundamentally reframe our place in the universe. The Copernican revolution demoted us from the center of the cosmos. The discovery of exoplanets showed us that our solar system is not unique. But finding a living, breathing world next door would be the final step in our cosmic maturation. It would prove that life is not a fluke, but perhaps a common, even inevitable outcome of cosmic chemistry. It forces us to confront the Fermi paradox. If life is common, why is the universe so quiet? Where is everybody? Perhaps civilizations rise and fall in the blink of a cosmic eye. Perhaps the gulfs between stars are simply too vast to cross. Or maybe the universe is not silent at all. Maybe it is a library of whispers, and we are only just now learning how to read the language and listen to the stories. GJ251c is one of the first intelligible words we have managed to decipher. The existence of such a world also holds up a mirror to ourselves. In our search for habitable worlds, we are forced to define what makes our own planet so precious. We study the delicate balance of our atmosphere, the cycling of our oceans, the intricate web of our biosphere, all in an effort to understand what criteria to look for elsewhere. This outward gaze inevitably turns inward. It highlights the profound fragility of our own habitable world, a planet we are actively altering through our own actions. Perhaps the greatest lesson from finding another Eden is a renewed appreciation for the one we already inhabit. The journey to GJ 251c is for now a journey of light and data of photons and gravitational waves. It is a pilgrimage of the mind undertaken by scientists and dreamers who look at a faint point of light and see the potential for oceans, continents, and life. This world 20 light-years away is a potent symbol of our own relentless curiosity. It is a testament to the human spirit's refusal to accept that we are an island in an empty cosmic sea. We do not yet know if it is a barren rock, a water world, or a true cousin to Earth. We do not know if anything stirs on its surface or swims in its alien seas, but for the first time we know where to look. The silence from the universe has been broken not by a shout but by the gentle rhythmic tug of a world on its star. It is an invitation, a challenge, a whisper across the void waiting for us to listen more closely, to look more deeply, and to continue the search for an answer to that most ancient and human of all questions.